Hi everyone, my name is Hannah Williams and I am a software engineer working with Dell Technologies, working on BIOS for Dell switch platforms. My talk today is on enhancing secure boot in ONIE. What is secure boot? It is a framework for verification of firmware and operating system on a platform and prevents system from booting when these components are compromised. It enables verification of components in the boot chain, starting from a root of trust. The root of trust is important and must be immutable, or in other words, something that cannot be changed. Why do we want to enable secure boot on networking platforms? Malicious code running on a compromised network device can cause denial of service, access privilege escalations, allow data stealing. These are just a few examples. Often software vulnerabilities are what open the doors for malicious code to enter a platform. Consider the scenario: a software vulnerability was found, so the next step would be to make a fix available as an update. When an update is available online with a fix for this vulnerability, how can you be sure that this software is the genuine original one that was intended by the manufacturer and not modified maliciously? For example, if it was a OS ISO image, it could have been unarchived and components within it could have been modified with malicious code and then repackaged again. How can we detect this? This is where Secure Boot comes into the picture. If the OS image was signed and if the platform has Secure Boot enabled, then this malicious OS image will not boot. Better yet would be to have verification enabled during the download and installation itself of the OS. But this kind of a verification can only be trusted if we have the verification software running in an installer on a securely booted platform. Let's quickly look at possible attack surfaces on a network platform. Spectre and Meltdown are examples of hardware vulnerabilities mostly caused as a side effect of out-of-order execution and speculative execution. So the CPU itself is an attack surface in this case. BIOS can be an attack surface too. If BIOS fails to lock down some of the configuration registers, these can be exploited. System management mode is another attack surface. Since SMM is a privileged execution mode, vulnerabilities in this mode can become a tool in the hands of a malicious user who can use it to inject malicious code. For example, it can turn off locks that may be set by BIOS. For example, if flash write protection is turned off from within SMM, then malicious code can get written into flash. Malware injected into flash is persistent, so even a reboot will not fix the problem subsequently. Next, DMA attacks, where DMA from a peripheral device can corrupt memory because of incorrect IOMMU config, is an attack surface. Malicious code can be injected this way into memory. Grub shell with its extensive command set is an attack surface, and so is allowing kernel command line to be modified or edited from Grub. This can be used to, for example, restrict the number of CPUs allowed for use by the OS and thereby slow down the system, for example. You can also change the path of the kernel and init ramfs from the default ones through Grub. We look at how we can lock down attack surfaces in ONIE. How does Secure Boot help? We have the assurance that software running on the system is from a known source and is authenticated and is not modified maliciously. It prevents malware injection through firmware or OS images that are loaded during boot time. ONIE is a Linux-based operating system that is used to install the target operating system on a network switch platform. The target operating system could be fetched from a web server. To make sure malicious target operating system is not installed, ONIE should have Secure Boot enabled. Only if ONIE is part of a Secure Boot chain, it can then be used to verify other components that are installed using ONIE. It also can be used to securely enroll revoked keys onto platform blacklist database and to enroll new keys into whitelist database for a new target NOS. What does secure boot in ONIE look like? Let's look at this boot chain. BIOS is the root of trust here. The BIOS or the boot block or startup code in BIOS should be made immutable as it is the root of trust and carries the key to verify the next stage. In some cases, there can be other immutable code that runs before the main application processes BIOS, like BootGuard, ARM Trust Zone, AMD PSP. The unmodifiable code in them starts up first and verifies the BIOS or the startup code within the BIOS, which can then be used to verify the next stage in the chain. In the absence of these additional microcontroller or processors that do the verification, effort must be taken to make the startup code in BIOS read-only. BIOS is the root of trust in this example. BIOS will then verify and load Grub. Grub will verify and load Grub configuration, Linux kernel, and init ramfs. ONIE should have password enabled and also having file system encryption when you use a root file system. In the case of NOS, will enable an end-to-end secure system. To summarize, every stage starting from a root of trust verifies the next stage and stops when the next stage cannot be verified. In the previous slide, BIOS booted Grub, but when you use Microsoft Authenticode signing, you cannot sign a GPL component like Grub. And so to work around it, shim was invented. Shim can be signed using Microsoft Authenticode signing. BIOS would have the public key that is needed to verify shim and loads shim after verification. Shim will then verify and load Grub. The keys that can be used in shim to verify Grub can either be a key embedded while building Grub, while building shim, or it can be the UEFI DB key present in BIOS or the mock key. So one of these three keys can be used by shim to verify. The mock key can be added using mock manager. Shim provides a shim lock UEFI protocol. Grub uses the shim protocol to verify Linux kernel, but it does not verify init ramfs. If you enable secure boot in ONIE today, it uses the shim and only verifies Grub and Linux kernel. Here is a quick note on signature generation. This has been taken from the UEFI spec. Hash of the image is generated first using a hashing algorithm. The private key of the signature algorithm is used to encrypt the hash. This is the signature of the image. The signature is embedded in the original image, or in some cases, it can also be present as a detached signature. The public key is embedded into the previous layer of the boot chain. This explains signature verification. Now, the signed message has two components: the message itself and the signature. The signature in the image is decrypted with the public key to generate the raw hash. Also, the hash from the image is computed. The two hashes are compared. If they do not match, then the boot process will not continue. EFI files, which are PE-COP files, have a header entry to store the signature. Other formats can still have the signature generated and available as a detached file. Here's a quick note on keys that are part of the UEFI framework. UEFI defines platform key, key exchange key, and DB key. The platform key is the root key. The key exchange key must be signed with the platform key and DB key signed with KEK. The DB key is the whitelist key database and is used to sign and verify the image. The DB key is part of the whitelist key database. There is also the blacklist DBX key database, which has the revoked keys. The private keys are used for signing and are kept secure. The public PK, KK, and DB keys are in BIOS. BIOS will use these public keys to verify new keys that are added to the system for signing, for verification of signing. The bottom right shows how the DB private key is used to add a signature at build time, and how the DB public key is used to verify the signature of the image at runtime. Keys can be built into the BIOS. Also, new keys can be enrolled from the OS. Runtime key enrollment is authenticated by BIOS. The blocks on the left here show how the keys need to be signed for runtime enrollment to be successful. Platform key is unique to a platform. Key exchange key must be signed with PK for enrollment to be successful. Whitelist DB and blacklist DBX are signed with KEK. DB key is used to sign the image. And by putting a customer's KEK on the system, you can allow, for example, the NOS vendor to own generation of DB keys signed with their KEK. How to enable secure boot in ONIE? Here's what we can do. These variables should be added to your machine.make file in your specific for your platform. Secure boot enable equal to yes has to be set to enable secure boot in the build, where it will look for public keys to embed within an image and then use private keys to sign an image. There are two sets of keys shown here, the mark key pair and the DB key pair. In ONIE vendor cert file, the dir one uses, it's actually the public key which is embedded inside shim and which will be used to verify grub and kernel. So this will be part of the shim make file used, and it will be pulled in during when shim is built. So the ONIE vendor secret key pem file, I have used the mock private key, specified the mock private key for this variable. And this is the secret key of the mock key pair, which will be used to sign grub and the kernel. And then the other key I have used is the shim key. This shim self-sign secret key pem, I have specified, I've given the path to, I've given the, you have to specify the path to your, to a private key, and I have used the DB private key here. This key is for signing shim EFI file. However, if you decide to self-sign, you can add the key here. The other case would be to send shim to Microsoft for signing, and then you get back the signed image, which you can pull into ONIE. Instead of a mock key and DB key, like I have shown above here, you could just use the UEFI DB key in both these cases. Here is a pictorial summary of the previous slide. Public DB key is embedded in BIOS, and shim is signed with the private key of the pair. Shim has an embedded mock key. Grub and kernel can be signed with either of mock key or DB private keys. Grub uses shim to verify kernel. However, shim does not verify init ramfs. Here are some issues we saw when we enabled the existing ONIE secure boot. UEFI BIOS was able to verify and start shim, and shim verified and started grub, but grub did not verify the signed kernel. We had to add the verify module in grub to get grub to verify kernel. Also, when the kernel had an invalid signature, when grub uses shim to verify, there was a crash that we saw. Also, the current version of Grub in ONIE is 2.02. The current one, there is a newer 2.04. We use 2.04 for our testing, and in 2.04, you need to use the shimlock Grub module. So we had to add a few extra Grub patches to get Secure Boot working. Proposal for changes in ONIE. Here is a high-level look of what my proposal is. We should make shim optional. So for this, we need to add a skip shim variable. This is for those who self-sign and don't use Microsoft signing. Add GPG key to Grub to also verify init ramfs in addition to kernel and grub.cfg. If you remove shim, you will then need GPG key added to Grub to verify kernel and init ramfs. Even if you use shim, you can still add GPG key in Grub. Add scripts to verify NOS image and firmware updated image before executing them using ONIE NOS install or ONIE firmware package. Also, the other thing is to add scripts to enroll revocation keys or new keys for any NOS. So specific to Grub, these are some changes we can make. Add Grub version to select a specific version of Grub. So we can select between, for example, 2.02 or 2.04. Add GPG public key to Grub, which implicitly sets check signatures equal to enforce within Grub. So this will in turn require the additional variables to be added because we need GPG keys to be pulled in to ONIE build. So we would need a GPG enable equal to yes, no, and then the paths provided to the GPG public key and the private key. Check signatures equal to enforce means Grub will verify every file it loads with the GPG public key. This means grub.cfg, grub env file will also be verified in addition to Linux kernel and init ramfs. This also includes any chain loaded files. So the other thing is to add a use Grub Standalone option. This is for Grub to be built as a standalone module so that Grub modules do not need to be individually signed. The single Grub binary can include an initial grub.cfg, which can specify where the root is and the location to your main grub.cfg. Since this Grub has a public key embedded, it will require every file it loads, including grub.cfg, to be signed. Again, these can be made configurable. If someone wants extra protection, then they can enable these new features. Verify NOS installer image before executing it using ONIE NOS install. Since we have booted securely until this point, we can trust ONIE to verify signature of the installer binary. We will need to extract system DB key, for example, for verification. One way it can be done is by extracting the DB public key from UEFI database by using EFI tools, EFI readware. We will need to install EFI tools in ONIE for this. The installer binary can be then signed with the DB private key and the signature available as a detached binary for ONIE NOS install to verify. Again, we could use either GPG keys or UEFI DB keys or mock keys to sign and verify the installer. Verify firmware updater image. This same concept can be done for verifying the firmware files that are installed by the firmware updater. It is better to verify firmware before installing to avoid putting the system in a state that cannot be revived by the user. Add scripts to enroll keys. EFI updateware from EFI tools package can be used to enroll keys into UEFI key database. This way, if a vendor's KEK public key is embedded in BIOS, the vendor can then use this key install script to install new DB image signing keys. UEFI keys are authenticated variables. Hence, a properly signed key can be installed from the OS, and BIOS will verify before writing it to NVRAM. We also need to tie all secure boot features to a secure boot enable disable variable at the root of trust. In UEFI secure boot framework, there is a secure boot enable disable variable that cannot be modified runtime and would need console access to be modified by going into setup menu. When a customer has trouble with incorrectly installed software, there would be a need to disable secure boot to reinstall software. This is where the secure boot enable disable helps, but care should be taken to also not allow the state of this variable to be modified by a malicious user. A physical access to modify this variable is acceptable, but not a runtime access. There are some workarounds needed if you set GPG enable equal to yes. Grub.cfg cannot be modified runtime from ONIE update installer or NOS installer. This is because Grub.cfg has an associated signature that was generated during ONIE build time, and modifying it runtime will cause verification to fail at boot time. This can be worked around by making your grub.cfg in ONIE, ISO, or ONIE updater, or your NOS installer to be dynamic. For example, it can have functions to look for specific labels on a platform boot media and add menu entries for them using pre-programmed menu functions. Grub install cannot be used as is from installer. Instead, we need to modify the install script to add lines to copy the required files. So grub EFI file has to be copied and the signature file that goes with it. So the detached files for grub EFI and grub.cfg will have to be also copied. If you use standalone grub, you do not need to copy the individual grub modules. To summarize, ONIE build must be modified to generate these signatures during build time, and the runtime install scripts have to be modified to install the signed images at runtime. On system boot, the signatures will be verified. Here is an example of how GPG key can be generated and then used to sign kernel and initrd from within ONIE build. Here are a few helpful links. I need support from the community to add these changes into ONIE and to enhance existing secure boot in ONIE. This can also serve as an example for any NOS to enable secure boot. So together we can work to bring in these changes and enhance the existing secure boot in ONIE. Thank you.